Hello, fellow math enthusiasts, linear functions and models. Put the equation below in slope-intercept form and use function notation. So we have this equation, 2x plus 5y equals 8. You might recall from an algebra class in the past that commonly lines are written in this form here, y equals mx plus b. This is called slope-intercept form. This is what we're after. The way to get there is to simply solve this equation for y. So I'm going to begin by subtracting 2x from both sides, and I'll write that term first, and then the plus 8, and then divide everything by 5. So y is equal to negative 2/5 x plus 8/5. So this is slope-intercept form. Use function notation. And just for clarity, y equals mx plus b, this is our slope-intercept form because the m reveals the slope and the b is the y-intercept. Very easy to confirm when you plug in 0 for x. That makes this part here 0 out, leaving you only b. So 0 comma b is a point on this graph, hence we call b the y-intercept, and m will be the slope. Use function notation, so I write this instead as f of x equals, and then I'm just going to copy this here. Okay, so there's the first step. Determine the slope of the line. So the slope of the line is the coefficient of x. We'll write that as the m equals negative 2/5. Determine the intercepts of the function. So that means the x and the y-intercepts both. So if I'm going for the y-intercept, you just have to plug 0 in for x. And that, of course, is going to just give you this 8/5. So that tells us that the y-intercept is the point 0, 8/5. Let me go ahead and place that in our graph right now. 8/5 is 1 3/5. And if I were to break this little interval up into fifths, so 1 3/5 would be about right there. So there's the y-intercept. To find the x-intercept of a function, you set the rule of the function equal to 0, and the rule is negative 2/5 x plus 8/5, and solve this for x. Another way you could do it is you can effectively take this equation right here before we wrote it in function notation by solving for y. And if you're looking for an x-intercept, you can change the y to 0 and solve for x. You're going to see how easy that is. If you just change the y to a 0 in this equation, this leads to 2x equals 8. In other words, x equals 4. So 4 comma 0 will be a point on this curve. But I'm going to go ahead and do it by set the rule of the function equal to 0 and solve for x. I notice that there's two fractions involved here. They both have a denominator of 5. So if I take this equation and I multiply both sides of it by 5, that'll get rid of the denominators. 5 times 0 is still 0. 5 times negative 2/5 will be negative 2, so negative 2x, and then plus 8. Then add the 2x over, and then divide, and we still get this 4. So all this information tells us that 4, 0 is a point on our graph. And this will be a line because it has the general structure mx plus b. So once you have 2 points, in this case the intercepts, we can go ahead and make a line. Determine the domain and range of the function. Actually graph the function first, but finding the domain and range are more easily done once you have the graph in place anyway. The domain is every single x that's allowed to be plugged into this function. So if you just look at the function rule right here and say, hey, is there anything I can't do negative 2/5 of? And the answer is no. You can negative 2/5 of any number. There's no restrictions on what x can be. So the domain is all real numbers. Remember, you can say domain is all real numbers is a fast way to write that, or you can instead write negative infinity to infinity. And the range is all the possible y-coordinates, but this line is diagonal, it's not horizontal, so every possible y-coordinate will be achieved at some point. In other words, if you were to make a horizontal line scanning through the graph, every horizontal line would hit the black diagonal line somewhere, right? Maybe off of our particular window. This is to suggest that our range is also all real numbers. All y-coordinates are possible. So there's our domain and range of this function, and we have the graph. Now I want to make a few comments about slope. We know that the slope is negative 2/5. That negative can be associated with the numerator or with the denominator. And as far as slope is concerned, you do want to think in terms of rise and run to understand exactly how steep this line is going to be produced. So for example, start at any point on the function. Let's start at this point right here. And let's take an interpretation that our rise and run are 2 and negative 5 respectively. So the negative is associated with the run. If the run is negative, it means you go left that amount, go left 5 units, and then the rise is positive 2, so I would go up 2 units, and that should take you back to the line. Right, another point on this line should be right here at negative 1, 2, because I went left 5, and then I went up 2, a rise of 2. A run of negative means left, and a rise that's positive means go up. So once you have this staircase idea in play, you could repeat it and find another point in the line off our image. You can just keep doing this sort of staircase from point after point after point. You could start with the y-intercept and do the staircase and find another point. Between any 2 points, if you go left 5 and up 2, it'll go back to the line. Another way to interpret this slope is by associating the negative with the rise. So looking at this one right there. So the run is positive 5 and the rise is negative 2. So if I were to start at a point, let me start at this point and run to the right 5. So a positive run means go to the right, but then a negative rise means drop 2. So we have a negative 2 rise, and that takes you to the 0.40. You can also think about the slope as a fraction over 1. The slope was negative 2/5, so you could think of that as negative 0.4 over 1, and think of the run as 1 and the rise as negative 0.4. So that would suggest that take any point on this curve. Let's start with this point here. Do a run of positive 1, so go right 1, and then do a rise of negative 0.4. And then if I were to copy this, I could repeat that, always go right 1 and go down 0.4, and do it from any point to find a second point. In fact, this is the most common way to think about slope, is that when I say the slope is negative 2/5, it means that for every unit to the right that you go by 1, you should go down by 2/5. As far as graphing this in Desmos, you can type in either the rule of the function, which was negative 2/5 of x plus 8/5. Right, so here's the line in question. You can also put an f of x equals in front of this, or a simple y equals in front of that. Equals, it'll graph the same thing, or you can write f of x equals. And you can also just type in the original equation, 2x plus 5y equals 8. You can see it produces the same graph. Let's go to the next slide. Find the rule of the linear function that passes through negative 2, 3, and 4, 7. So let me first graph these points. And we want to find the equation of this line here. And we want to find the rule of the linear function. So we want to get y isolated and write it as a function and figure out what the rule is. The first thing you want to do is figure out what the slope of this line is. And so to find the slope, you might remember this formula from the past. You do y2 minus y1 over x2 minus x1. Or you could say delta y over delta x is another way to write that. That triangle is a delta. It's a Greek letter. It's a capital letter. And it means change in. So change in y over change in x. I'm going to call this the second y-coordinate and that the first y-coordinate. So we do 7 minus 3 divided by, and then go in the same order. Second x minus first x. 4 minus negative 2. So that's going to be 4 plus 2. 7 minus 3 is 4. 4 plus 2 is 6. And so we get a slope of 2/3. Now there's a few ways to think about this. Slope is positive, so our line should be increasing from left to right. I'm going to interpret this 2/3 as the run is 3 and the rise is 2. So that means if you were to go right 3 and then go up 2, it would take you back to the function. And then of course you could do that again and connect ultimately the 2 points that we had in this. Just for the sake of argument, you could also say the slope is equal to negative 2 over negative 3, right? If they're both negative, then you would still say a slope is 2/3. And that just means that you would go a run of negative 3 followed by a rise of negative 2. Notice that still connects you from one point on the line to another point on the line. You could also interpret this as a 2/3 over 1, meaning that if you go over 1, you would go up 2/3. So go over another 1 and up 2/3 more, and that should take you to where the y-intercept is. That's one way to find the y-intercept. Let me show you another way. We're going to use something called point-slope form to create the equation of the line. It's y minus y1 equals m times x minus x1. This is called point-slope form, whereas the form up here, this one's called the slope-intercept form. This is a very useful form for finding equations of lines. Once you know the slope of the line connecting these 2 points, you plug that in for the m right there, and then for the x1, y1, you can use either one of these points. It doesn't really matter. So I'm going to use this one here as my x1, y1, and the y and x don't change. Those are the variables of the equation. So you get y minus the y-coordinate, and we're calling this 3 here y1. So y minus 3 equals m, which is 2/3, times x minus, and then we do x minus that x-coordinate. That would be x plus 2. And then distribute the 2/3, 2/3 x plus 4/3, and then add 3 to both sides. So when I add 3 over to this side, I need to add 9/3. We get 13/3 here. So 4 and a third is what 13/3 is. Remember that once you get into slope-intercept form, that the 2/3 is the slope and the 13/3 is the y-intercept. So that 13/3 is precisely where this function crosses the y-axis. Of course, at this point, you can get rid of that y and call this f of x instead. So this was the rule of the linear function that passes through these 2 points. It's easy to verify that it goes through the 2 points. All right, plug negative 2 in for x and see if you get 3 for y. So if you plug negative 2 in for this x right there, that gives me negative 4/3 plus 13/3 is 9/3, and that gives me 3. Let's test 4, 7. Plug in 4 for x here. 4 times 2/3 is 8 thirds. 8 thirds plus 13 thirds is 21 thirds, and 21 thirds is 7. And just to show you, you could have used the other point as well. It doesn't matter. Let me do the same thing, but use this point here in my point-slope form. So we have y minus the y coordinate is equal to the slope times x minus the x coordinate. Distribute the 2/3 across there. Y minus 7 is equal to 2/3 of x minus 8 thirds, and then add 7 to both sides. And 7 is the same thing as 21 thirds. Add that to negative 8 thirds, and that gives me positive 13 thirds. It doesn't matter which point I used. Find the rule of the linear function that passes through negative 1, 5 and 3, 5. So we're looking for this line. Now those 2 points have the same height. So when you do your formula for the slope, I leave it to you to verify this, but you'll find that the slope is 0. All horizontal lines have slope 0. And we also happen to know what the y-intercept is going to be. It has to be 5 as well. So you could just go straight to y equals mx plus b with this one and say, okay, well, y is equal to mx plus b, and I know the m is 0, and I know the b has to be 5, so this just produces y is equal to 5. And in function notation, it would be this, f of x equals 5. This is called a constant function. It's a function whose rule is just a constant. F of x equals 5 is a horizontal line, height 5. Now give an example of a line that is not a function of x. Well, the only kind of line that's not a function of x is a vertical line. So vertical lines are not functions of x. They're still lines, and they are functions of y, but they're not functions of x. An example of a vertical line, x equals 2. There is no y in the equation to solve for, and vertical lines fail the vertical line test. So horizontal lines are constant functions of x, diagonal lines are changing linear functions of x, and vertical lines are not functions of x at all. Determine whether each set of points represents a linear relationship. If so, find the rule of the function. Okay, so there's a few ways to do this. One is to plot the points in each table. And the question is, are these collinear? Meaning, do they represent a perfect linear relationship? Is there a line that can be drawn that would pass through all of them? And the visual would suggest that there is. It looks like all these points are on the same line. Well, the way to tell from the data whether this collection of data points represents points that are on a line is to look for constant slopes between any pair of points. And that can be done a variety of ways. Let's compare these points. The change in y here is 1.5 is what we gained, and the change in x is we gained in 3. So when I do a delta y over delta x, change in y is positive 1.5, change in x is positive 3. This is the same thing as 3 halves divided by 3. I get a 1/2 out of this. Or you could have also done this. Double the top, double the bottom, 3/6, and that's also the same as 1/2. So it looks like our slope is 1/2. You want to determine whether that seems to be true between all possible pairings of points. So let's go from this delta x and this delta y. To go from 2 to 4.5, we gain 2.5. And to go from negative 2 to 3, we gain 5. Delta y over delta x, 2.5 over 5. Double each, simplify. Yeah, this is still a half. Keep it up. So we go from 2 to 5, that's a gain of 3. Go from negative 2 to 4, that's a gain of 6. Do rise over run, 3 over 6, that's a half. Check, that works. Negative 2 to 5 is a gain of 7. 2 to 5.5 is a gain of 3.5. And 3.5 divided by 7 is, again, going to be 1/2. If you verify that all of these make the same slope, then it must be that all of these are collinear with this first point, which means that any other pairing, they're going to be collinear. Now let's look at the next table. So these are the points. I'm going to try to connect the first and last and see if we can make this happen. Kind of looks like it's not happening because there's a few points that are not on this line. Why don't you take a look at some rises and runs here, and you can see some inconsistency. We're going to see a right 1 followed by a down 2. If I keep that up, notice how it misses these other black points. Right, the line in question here, of course, is this line here, and it doesn't hit the other 3 black points. So it doesn't look like that these points are collinear, so there is not a linear relationship. And the way to say that this is nonlinear relationship, so I'm going to find the slope between these sets of points. So we have a delta y of negative 2 and a delta x of 1. So when I do the slope, rise over run, I get a slope of just negative 2. Now if I try to connect these 2 points, I'm going to get a slope of negative 2 as well. Same if I connect those 2 points, and same if I connect these 2 points, I'll get a slope of negative 2. But as soon as I try to connect one of these points to any of these 3, or this point to any of these 3, you're going to see the problem emerge. For example, let's try connecting the second and the third. Let's do that one. So to connect the second and the third, I see a drop of 4 and a run of 3. And the slope connecting those 2 points is negative 4/3. And that's not the same as negative 2. So we have inconsistent slopes between some of the points. This was a right 1 and a drop of 2. And compare that to the other, connecting the second and third, was a run of 3 that was, and a rise of -4. And they don't make the same ratio. The steepness of this line here is not the same thing as the steepness of that line there. Now back to the one that we said was linear, we need to find out y equals mx plus b. Well, the slope is 1/2. Think of this as rise and run. The rise is 1, the run is 2. So if you go over 2, you would only need to go up 1. And notice that would take us perfectly to where that y-intercept is. That y-intercept must be at 0, 3. And we know the slope of this line is 1/2. The b is going to be that 3, and the slope is 1/2, so you can go straight to y equals mx plus b form, because I know that the m is 1/2 and the b is 3. And of course, we'd want to use function notation here instead. The next slide. So there's two functions here, f and g. Graph both functions by hand. We're going to do that in a moment. Determine where f of x equals g of x. This is saying, do the two functions intersect with each other? And if they do, what are the x-coordinates where they do intersect? And so to find this by hand, you simply take the two function rules and set them equal to each other. Now, I don't like the fact that we have a fraction here. And when you have an equation and fractions, you can get rid of them all by multiplying everything by the lowest common denominator, which in this case is 3. So I'm going to triple everything first. That gives me 2x plus 6, or negative 3x plus 21. So now I'm going to add 3x to both sides and subtract 6 from both sides, and then divide by 5, and we get 3. Determine where f of x is greater than g of x. Here's f of x. I want that to be greater than g of x. This is a linear inequality. It's solved the exact same way you solve a regular linear equation. I don't like the fact that we have fractions, so I'm going to triple everything. You do have to remember the rule that when you're working with an inequality, and if you multiply or divide both sides of it by a negative number, you have to switch its direction, so be mindful of that. But multiplying by 3 does not change the direction. We get 2x plus 6 must be greater than negative 3x plus 21. I'm going to add and subtract, and adding and subtracting do not change the direction. So add 3x to both sides, subtract 6 from both sides, and now divide both sides by 5. This suggests that if x is bigger than 3, then f of x will be higher than g of x. So when it says determine where, whenever you see a where question about a function or a collection of functions or something, we're talking about x-coordinates. Give the x-coordinates where these things happen. And then the other one is less than or equal to. It's going to look a lot like this one here to get started, except this will be less than or equal to. I'm still going to triple both sides, but I want to show you a slightly different approach from there, just so you can be mindful of something that you need to be mindful of. Tripling everything first does not change the direction of the inequality. So we still get 2x plus 6 is less than or equal to negative 3x plus 21. But this time what I'm going to do is I'm going to subtract 2x from both sides. Now that's a different step than what I've been doing in the past, where I've been adding 3x to both sides. Remember, adding subtracting does not change the direction of the inequality. So sometimes people think that, oh, I subtract 2x from both sides, and they see this negative sign, and so they want to switch that, but don't. And I'm also going to subtract 21 from both sides. And notice what happens. We wind up getting 6 minus 21 is negative 15, less than or equal to, and negative 3x minus 2x is negative 5x. We are going to divide both sides by negative 5 to isolate the x. So we have to change that inequality in the next line. So negative 15 divided by negative 5 is 3, greater than or equal to, and then just x. Only when you multiply or divide both sides by negative, you have to change the direction of the inequality. So x has to be less than or equal to 3. I'm going to write x first, less than or equal to 3. Right, just make sure the alligator mouth is opening towards the 3. Now let's go ahead and graph these things. These are easy to graph because they're in slope-intercept form already. So the function f has a y-intercept of 2 and a slope of 2/3. That's a rise over a run. So the run will be 3. So I'm going to go right 3 and the rise will be 2. So that takes me to a second point, and then I can just graph the line. The g of x next has a y-intercept of 7 and a slope of negative 1. When the slope is negative 1, you can think of that as being over a 1, so that you have a run of 1 and a rise of negative 1. Y-intercept was 7, and we go right 1 and then down 1. If you do that a second time, it'd take you there. Do it a third time, it'd take you right to this point. And this sort of reveals where they're going to cross. Notice that they cross for the x-coordinate of 3, which is what we found here. The two functions are equal to each other when x is 3. You might then want to know, well, what's the y-coordinate where they intersect? Once you know that they cross at x equals 3, you can find f of 3 or g of 3, it doesn't matter, and you should get the same y-coordinate. Plug 3 in here. 2/3 of 3 is 2, and add 2, you get 4. Plug 3 in there instead. Negative 3 plus 7 is also 4. Also notice our inequalities can be answered visually as well. When it says, hey, where is f of x more than g of x? When you're on this side of x equals 3, f is higher than g. Or you pick any x-coordinate larger than 3 and plug it into both functions, and f will be more than g. And then they answer the other one, hey, where's f less than or equal to g? For f to be lower than g, we need to be picking x coordinates over here. And because of the partial equal sign, we have a partial equal sign here as well. If x is 3 or less, then the output of g will be greater than or equal to the output of f. Okay, last slide. A container initially holds 55 ounces of water. The container cracks at the bottom and begins to leak. 20 minutes later, the bucket contains only 40 ounces of water. Determine the amount of water in the container as a function of the number of minutes that has elapsed since the container began to leak. Okay, so we're going to use t for our independent variable for time. And then for the amount of water, we want a letter as well. Since we're talking about volumes here, let's use v. We'll say time 0 is when the water started to leak. At time 0, the volume was 55 ounces. And let's put our units above this. Time will be in minutes, volume will be in ounces. All right, so 20 minutes later, so when time was 20, the bucket contains only 40 ounces. Okay, so in order to create a linear equation that's going to model this, we have to make an assumption that's not stated here. We have to assume that the water is leaking at a steady rate, that it's losing the same amount in the same amount of time, that it's not speeding up or slowing down how much water it loses per minute. And so we're going to assume that it's leaking at a steady rate. To figure out that rate is to find the slope of the line that will connect these 2 points. So we're going to find the slope. We do change in v, so we do the 40 minus the 55, or I do v2 minus v1 over t2 minus t1. So in other words, we lost 15 ounces in the span of 20 minutes. So we can simplify this fraction to a per minute amount. Negative 15 over 20 is the same thing as negative 3/4 ounces per minute. You can think of that as you lose 3 ounces every 4 minutes, or you can think of it as you lose 3/4 of an ounce per minute. Notice that we have a v-intercept, 0, 55. So the 55 is going to be the b in our equation, and we just found the m. So we could now say v is equal to slope, negative 3/4, times the time, plus the b. And here is our function. It's a function of t, so let me go ahead and make that more formal and put v of t. Volume is a function of time. Determine how much water should be in the container 30 minutes after it started leaking. So in other words, after it started leaking, when t is 30, we want to figure out what v is. In other words, we just have to plug 30 into the v function. So we say it's going to be negative 3/4 of 30 plus 55. Now if you put units on all this stuff, this is ounces per minute. The unit on the 30 is minutes, and then the unit on the 55 is ounces. And when you multiply ounces per minute times minute, then you get ounces back. So the first product will give you ounces, and you add it to the other 55 ounces, and we get an answer that's in terms of ounces. Negative 3/4 of 30, it's negative 90/4, or you can write that instead as negative 45 halves. Let's just go ahead and do that. Plus 55, 55 is 110 halves, and add these together, 110 minus 45, so 65 halves ounces. And you can write that as 32.5 ounces. So 30 minutes after it started leaking, we expect there to be 32.5 ounces. Again, assuming that the leaking is happening at a steady rate. Determine when you can expect the bucket to be empty. So if the water keeps leaking, at what point will volume be 0? So we want v to be 0, we want to find out what the time is. You change the volume function to 0, and you solve for t. So I'm going to add 3/4 t to the other side, so we get 3/4 of t is equal to 55, and then multiply both sides by 4/3. Multiply 55 by 4/3, multiply 55 by 4, 220 thirds, and this is in minutes. Now this problem doesn't ask you to do this with Desmos, but let's go ahead and type this in. And we're going to have to zoom out quite a bit to see this. There's our curve. You can use this software to answer the questions like, hey, what's v of 30? So you could just type in v of 30, or you can write a vertical line, type in x equals 30, and that just gives you a vertical line that you can intersect with the green graph and say, hey, look, there's our answer for the first question. At 30 minutes after it started leaking, we expect the volume to be 32.5. Or you could have just simply set up here capital V of, and then put 30 in those parentheses, and it gives you that 32.5. And then when do we expect the volume to be 0? That's going to be this intercept over here. 73.3 repeating, essentially, which is exactly what this 220 divided by 3 is our, we'll say, approximately 73.3 minutes. Okay, and then here's how the technology helps us answer these questions. If I had asked you, how long does it take for the volume to be down to 10? Then you change v to 10 and solve for t. Or you could do a horizontal line, y equals, and put 10, find that point right there. And that tells me that when t is 60, v, the volume, will be 10. So 60 minutes after it started leaking, or an hour after it started leaking, the volume will have dropped to 10 ounces. Okay, this wraps up our lesson on linear functions and models.